Welcome, everyone. We're starting a new topic, gases. Before we delve into gases, I just want to review two things. The first thing I want to review with you happens to be the difference between evaporation and vaporization. What we learned before is that evaporation actually takes place on the surface of a liquid. And that's the only location in which it occurs. In addition to it only occurring on the surface of a liquid, we see that evaporation can actually occur at any temperature. Now, when we contrast that to vaporization, you should remember, is that vaporization actually takes place within the whole liquid. Not just the surface, but the center, the bottom, the sides, everywhere. In addition to occurring within the whole liquid, it actually only occurs at vaporization point or boiling point. It's the only temperature in which we can actually see vaporization. Other temperatures you wouldn't see vaporization occur at all because it is at this very specific temperature. All right, now let's also review the general properties of a gas, just because we learned that before. When we talk about gases, we should remember that gases generally have weak or no intermolecular forces. In addition to that, they have the highest kinetic energy. That's why in the image they're moving around. And they also have the highest potential energy. You should also remember about gases is that they completely fill any container that they're put into. And that's specifically because they have no definite shape and no definite volume. All right, with that review over, let's start with a brand new term. The first term I want to introduce is something known as an evaporated vapor. And oftentimes we get rid of the word evaporated. It's assumed that you know that it is an evaporated vapor, and we just say vapor. A vapor refers to the gas phase of a substance that is ordinarily a solid or a liquid at room temperature. So as an example, we can see that water at room temperature is a liquid. It just happens to be that's the phase at room temperature. But when we change this liquid into a gas, we can say that that's the evaporated vapor, because normally water doesn't exist as a gas unless I do something to it. Okay, now we have to introduce other terms too. The next term I have to introduce happens to be an open system. Now, let's set this up with a little story. So this is going to be a liquid of some sort, since we're talking about evaporated vapors. Let's make that a liquid. And that could be liquid X. Now we said that on the surface of liquid X, we're going to have evaporation. So these are my particles at the surface of the liquid that happen to be liquid. And on the surface, these little particles actually gain enough energy, specifically kinetic energy, to escape the liquid. So we're going to see them come out of the liquid because they've had enough kinetic energy and they can go and move out of this liquid phase. When they escape, they are now known as our vapor. So these are now our vapor particles. Now, what happens at this point is in an open system, these vapor particles are free to move out of this little container. So we see the vapor actually lost to the surroundings. Because nothing is there as a physical barrier to keep them within or very close to the liquid. So eventually in an open system, we see that things are lost to the surroundings. And in our case, since we were talking about vapors, the vapor particles that escape the liquid actually get lost in an open system. We can't contain them. Now, to contrast an open system, we now look at a closed system. In a closed system, what makes it different is that we are now going to add a lid or some type of physical barrier that separates our container from our surroundings. So I'm just going to label it as a lid. Now the setup is exactly the same. We're going to set up a liquid in this beaker, and it's still going to be liquid X. And the same process is going to happen. We're going to have these liquid particles at the surface actually gain enough kinetic energy to undergo evaporation. So there's evaporation occurring. And when they evaporate off the surface of the liquid, we now have our vapor. So these are our vapor particles as well. Now, something happens in a closed system that's different from an open system. These vapor particles eventually want to travel out, just like they did in the open system. But here, in this case, unfortunately, we have a physical barrier, which happens to be that lid. So the particles actually get trapped on the lid and turn back into a liquid particle. And you start to see liquid kind of condense, and that's the right word, on the top of the lid. So in a closed system, we see evaporation, but we also see condensation. And that's what happens in a closed system. Since a closed system doesn't allow things in or out of the system, you tend to see something else happening. And in this case, we see evaporation that occurs on the surface of the liquid, but then we also see condensation on the lid. Now, eventually what happens in a closed system, specifically in a closed system, because we have this physical barrier, we tend to see evaporation and condensation occur. What happens is that as we increase evaporation and as we increase the concentration of our vapor molecules, we also increase our condensation. In a closed system, when we have condensation actually equal, so the rate of evaporation, when it actually equals the rate of condensation, we say that this system, that's an N at the end, this system is in a state of equilibrium. And that eventually occurs because of that physical lid or physical barrier of that lid. We're not allowing things out, but also not allowing things in. In an open system, since there is nothing to stop the particle or the vapors to leave, we tend to see a lot more evaporation than we do condensation. So an open system never really reaches equilibrium like a closed system will. Now finally, we have one last term to introduce, and that happens to be vapor pressure. In a closed system, and we're going to talk about a closed system, eventually all of these vapor particles are sitting on the surface of the liquid. And this vapor has the same properties of any gas that we talked about. They're going to be constantly in motion. They're going to be constantly randomly moving around all the time. And as they move around, they tend to push on the container and also back on the liquid because they're constantly moving around. They have no intermolecular force. So by definition, when we talk about a vapor pressure, we're really talking about a force from a vapor that pushes on a liquid and against the walls of its containers. So it doesn't just sit there happily and do nothing. This vapor that collects above the surface of a liquid is constantly moving and creates this pressure or force by bouncing on the container or bouncing off the container, by bouncing off the liquid. Now you should know that vapor pressure of a liquid is not dependent on the mass or the volume of the liquid. So you're going to always see vapor pressure no matter how much liquid it is. So I could have a closed system just like this and still have a little bit of liquid and still have vapor pressure. So we notice that the mass or the amount of the liquid and the volume of the liquid does not matter. What we're going to see is that vapor pressure actually is dependent on the nature of the liquid, what liquid we actually have. And vapor pressure is also dependent on the temperature of that liquid. All right. So we'll talk about that in the next lesson. That's it for now. I'll see you.